I'm Laur Hesse-Fisher with the MIT Environmental Solutions Initiative, and this is Today I Learned Climate. Today we're talking about desalination, turning water into fresh water so that we can drink it or use it to grow crops. And we're talking about this because in many parts of the world, fresh water is getting harder to come by. So is converting saltwater a good solution? My guest today has devoted his entire career to this question and its relationship with climate change.
My name is John Lienhard. I am the Abdul Latif Jamil Professor of Water and Mechanical Engineering at the Massachusetts Institute of Technology. So climate change has a combination of effects on our fresh water supply. Patterns of precipitation are changing. We are seeing more frequent and longer droughts, and because warm air holds more moisture, we are seeing much heavier downpours in many places as well.
The trouble is that even if the total rainfall in your area is the same year over year, rain is coming more often in boom and bust cycles, sudden floods, than long droughts.
One of the ways we've dealt with the cycles of precipitation is by building reservoirs and water storage facilities of some sort. But when droughts start lasting longer, the reservoirs start to be depleted. We've seen this in the southwestern U.S., where the levels of two enormous reservoirs, Lake Mead and Lake Powell, have been dropping dramatically. If you go down the Colorado River, where both of those reservoirs sit, you'll find communities all along the way that are having to adjust to the reduced flows of the river.
And these changes are happening while the need for water is steadily growing. The United Nations, in its most conservative estimate, predicts that there will be about 1 billion more people on the planet in 2050 than there are today in 2023. We will need more fresh water than ever before. But many places are finding that they don't even have the same steady year-round supply that they used to. And there's a very tempting place to look for getting more fresh water.
Roughly half of humanity lives within 60 miles of the ocean, which means that for that half of the human race, there is the possibility of using seawater desalination to help meet the needs for water that are driven by a more variable climate and rising population.
About 98% of water on Earth is saltwater. So why don't we just do this for all the water that we need?
The problem is that it takes a fair amount of energy to separate dissolved salt back away from water molecules. And I'll give you an example. Suppose you're a bratty little kid at the dinner table and you have a glass of water and a salt shaker. And you decide that it would be very funny to dump the salt shaker into your glass of water. And you stir it up, and then Mom comes in. Mom says, "What did you do? Undo that. Get the salt back out." That's not so easy. That's the principal challenge of desalination.
Still, people have been trying to draw fresh water from the ocean for thousands of years.
Desalination goes back to ancient mariners sailing in the ocean and wanting fresh water while they were out there. The earliest means of desalination would be to take a kettle and build a fire under it, put in salt water, start boiling the water, and then put something above it to catch the water vapor and condense it as it comes out and capture it in some kind of a container.
Yeah, salt doesn't boil away with the water. Turn salt water into steam, and that steam is actually fresh water. Boiling, capturing, and condensing water is, as you imagine, a lot of work. And it was only about 60 years ago that anyone came up with a totally new way to get fresh water from the sea.
The first reverse osmosis membranes were developed at UCLA, my alma mater, by the way. Reverse osmosis doesn't involve heating the water at all. It involves pressurizing the water.
And to understand how this works, we're going to take a quick mental tour of a modern desalination plant. So, imagine you're standing on a beach, a few hundred yards from the shore. Behind you is a desalination plant about the size of a small factory. And in front of you, you're looking at a big pipe going out into the ocean, maybe just wide enough for an adult to stand inside. Inside that pipe is a pump slowly pulling in seawater.
The first thing you would encounter if you were flowing with the seawater is some type of a screen. And the screen's there to protect marine life. You don't want to be pulling fish into the desalination plant. Then you will encounter different stages of filtration. All of that's intended to eliminate other things that are suspended in seawater, whether it's silt or algae or something else of that nature.
This water is still full of bacteria and other microorganisms, so the next step is to chlorinate it to kill them off, and then dechlorinate it so that the chlorine can't wreck the rest of the machinery.
And so everything that we've done so far has been low pressure. Pressures, it might not be different than your garden hose. Now you come to high pressure pumps, which are large, very high efficiency, very high power pumps. So at that point, the seawater confronts the membranes.
These membranes are where the reverse osmosis happens. They have a static charge that keeps salt from passing through as the seawater gets pushed against it.
You're effectively squeezing pure water out of salt water.
And now this pure stream of fresh water can be piped out to homes and farms and wherever else it's needed. But wait, let's not forget the stuff that's left behind.
You didn't take all of the water. You took, for seawater, 40 or 50% of the fresh water. You left the remaining 50 or 60% of the water with the salts in what's now called a brine stream. What brine means is water with a lot of salt in it.
Which means a desalination plant has to constantly get rid of this brine.
And so the immediate question you're going to have is, gosh, how is that done, and is it safe? High concentrations of salt are not good for living things in the ocean, and salty water is heavier than fresh water. This means that it tends to settle, fall to the bottom. The fact that the heavier water falls in the ocean means that you need to ensure when you discharge salty water into the ocean that you're not letting it settle onto the bottom and just flow along like some blanket of salty water.
You can do this in a couple ways. A lot of desalination plants are located next to power plants because coal, gas, nuclear plants all need water to cool their equipment. So the brine from these desalination plants can be mixed with the used water from the power plants, and then it's not so salty when it flows out into the ocean.
If you're not at a power plant, what will be done is to take the water out to sea and to inject it upward with a set of nozzles that are distributed over a large area, several acres undersea, and which then spray the water in an upward direction so that it mixes in a cloud and dissipates. That usually gets the salinity of the seawater back to an acceptable level. So if the plant is designed properly, harm to marine life is minimal, if any.
The ocean isn't the only source of salt water. You can draw from salty groundwater as well. And in this case, brine is injected back underground or into a kind of pond where it evaporates and leaves dry salt behind. Today, desalination is used all over the world to the tune of over 25 billion gallons of water every day. That's about 1% of the water that the world consumes annually.
Desalination has been done and is done at a large scale in many countries around the Middle East, the Arabian Gulf, Mediterranean, the Red Sea. Those are areas that are very arid, that have significant populations, not a lot of freshwater resources. Desalination is widely used in Spain as well, and at large scale in China and India. The second largest producer of desalinated water in the world, get ready for it, is the United States.
Yeah, the largest desalination plant in the Western Hemisphere is a seawater plant outside of San Diego, California. though desalination plants can be found all over the country, especially in Florida, California, and Texas. So what's stopping us from using it everywhere? Well, to answer that, let's go back to our tour of a desalination plant. You notice that there's a lot of equipment there, pumps and pressurizers, and they use energy. How much energy?
All in, the energy cost for desalination is about 3.5 kilowatt hours per cubic meter at a modern desal plant.
Can you help us understand that? Kilowatt hours per cubic meter?
1 kilowatt hour is like running a toaster for an hour. A cubic meter is, if you like, 265 gallons of water.
The average American family uses more than 300 gallons of water a day. So we're talking about running a toaster for 4 or 5 hours every day to give a family their day's worth of water. And that's for seawater. If you have a good source of groundwater, that can take just 10 or 20% as much energy to desalinate. So this isn't a lot of energy in the context of our whole power grid. We wouldn't have to add that much electricity to provide the whole United States with desalinated water. But it is kind of a lot compared to the other ways of getting water. And that's important because energy isn't free. Whether desalination is worth it depends on what other options you have.
Desalination is one tool in the toolbox of integrated water management. You look at conservation before you do anything else. Look at how you're using water. In Las Vegas, Nevada, they are pushing very hard to reduce garden usage of water. They're asking people to tear out lawns, to plant things that are better aligned with the local climate. Don't try and reproduce the gardens of South England when you're living in the deserts of Nevada. Or build an aqueduct. In California, for instance, they built aqueducts all over the state because there wasn't enough water for the communities in, say, LA. Look at wastewater reuse when it's available. Reusing wastewater takes a lot less energy and costs a lot less than seawater desalination. And if all of that still doesn't help you meet your need, then you might start looking at the salty water nearby and saying, can I take the salt out of this so we can meet our need? By the time you're at that point, you have exhausted what you can do with cheaper resources.
Let's also not forget that we don't want to have to find new ways of getting fresh water. It's going to be harder. It's going to be more expensive. And the more we can limit future climate change, the better off we'll all be. So today you learned about desalination, how it works, and how we might use it as a tool in our tool belt today and in the future. That's it for this episode. We have links in our show notes to more places you can learn about desalination. We also have an educator guide with some classroom activities. You can find all that at tilclimate.mit.edu. TIL Climate is produced by the MIT Environmental Solutions Initiative at the Massachusetts Institute of Technology. David Lishansky is our editor and producer. Aaron Krol is our scriptwriter and associate producer and did our artwork. Michelle Harris is our fact checker. Sylvia Scharf is our climate education specialist. Ilana Hirschfeld is our production assistant. The music is by Blue Dot Sessions, and I'm your host and producer, Laur Hesse Fisher. Thanks to Professor John Lienhard for joining us, and thank you for listening.